So the first question is, when clicking on a pixel, you have this time series appear. Is it possible to change the time range for the time series where you showed it was from 1940s to present?
No, for the moment, we cannot change the axis and how the graphics are displayed. It, it, it would be a nice feature to have, but let me just check what I'm saying, but I guess for the moment we can't. No, it's just to give an overview of the time series. It's a quite recent feature, but it's a good feedback to have, and we can share it with our internal team to enable what you are requesting.
Okay, thank you very much. Okay, next question is, why not all data can be visualized in the viewer tool? Is there a plan to include all data sets, especially in atmosphere and GAMS?
Well, I'm not sure if I'm the right person to ask, but basically the data are viewable because uh, there is some, like I said, the WMS service allows to show the data and to visualize data on a tool. I'm not sure if WEkEO is using the same protocol, but basically it's just that not all datasets provide the protocol WEkEO is using to visualize the data on the viewer. And but I don't want to share some incorrect information, so I won't enter into more details. But maybe if you really want the information, maybe just ask the question in the widget chat, and we will ask the question into our expert team.
Yes, we will add more detail about this in the post-event report that we will send.
Yeah.
Thank you. Next question is, I noticed that some datasets from the GLOW FAS are included, but not all of them. Is it planned to add more? And basically it's the same question from before.
Yeah, so it's quite the same answer I'm going to to share, because the thing is that WEkEO is a platform that gathers and distributes the data coming from the different Copernicus services, Sentinel included. And basically, we will have to ask the provider and our internal team once again to know why these datasets are included and the others are not. Honestly, I don't have the answer. I guess there is a reason, but I don't have it.
Yeah, we'll ask about this. Next question is, does this WEkEO data viewer provide some unique data sets compared with Google Earth Engine?
To be honest, I don't really know, and I didn't really browse the Google Earth engine. But as I just said, WEkEO provides the dataset from all the Copernicus services and some others, like Sentinel data or Spot data. But I can't really answer this question because I don't know what we can find on Google Earth Engine. But I would say no. Basically, I would say there is no unique dataset on WEkEO because WEkEO just provides the data from the different partners and the different Copernicus providers. So I don't think there are unique datasets on WEkEO.
Okay, thank you. The next question is, can you download the map for use in ArcGIS?
I'm not sure to understand the question because I'm not sure to understand what download the map, what the user has in mind with download the map. What you
I
can
think
do,
they mean download the map directly from the viewer, which is not possible.
I know. We can't download the map like we are seeing on screen. But in ArcGIS or other GIS tools, what you can do, like I have presented, is to take the WMS, WMTS link. So on the dataset, you go on the tab I shown, and you can paste this link to ArcGIS. So you can visualize data like that. But I don't think you can download the map you are seeing on screen, if it's your question.
Thank you. Next question is, why can't I plot tropomy data in the map? I can only order it. It would help a lot to actually plot the measured data, sorry.
Well, I think it's the same question as the first or the second one.
Yeah.
Not all datasets, unfortunately, are viewable on the map. There are some reasons, but I can't give them for the 500 datasets. So uh, I can't answer this question. I can just
That's okay.
say that yeah, some datasets are viewable and other are not. And if you want to visualize the data, you need to download them and to plot them programmatically or in a GIS tool.
Which we will show just after that with some
Exactly.
tutorials. Okay, thank you. And yeah, the last question is, can you show it doing with NDVI, and what is the timeline available for the data from start? I guess it really depends on what data we're looking at.
Yeah. I will just invite you to type NDVI in the free text search bar. I guess there are multiple datasets with NDVI. Maybe today I would recommend let me check, the GRC dataset. Yeah, so we will maybe share the answer later. But if you type GRC in the free text search bar, you will have one dataset left, the CLMS geophysical parameters. And I guess that in this dataset, sorry, you will have the NDVI. And then to answer about the time range of the datasets, you have the details when you open the description of the datasets. And now I can see it's from 1992 to today. So 2023 will be available for these datasets.
Okay. Well, thank you very much. That's all the questions we received today. So thank you for your presentation and for answering questions.
You're welcome.
We will now go to the next presenter, who is Noemi Fazzini. Hi, Noemi.
Hi, hello everyone. Thank you for being here today.
Yeah, sure. So Noemi is a data scientist at the Meteorological Environmental Observation on behalf of EUMETSAT. And Noemi, you will be presenting or like doing the demonstration of a Python tutorial. So whenever you're ready, the floor is yours.
Okay, thank you, Mary. So hello again. Today I will let you see the Python tutorial about the use case we decided to show, which is wildfires monitoring in Spain during the season of 2025, specifically in August of 2025. But before jumping right in the Python tutorial, I just want to give you a quick overview of the functioning of the workspace. So this is a Jupyter Notebook for those of you who aren't familiar with them. On the left side, you can see some panels. If you click on the folder here, you can see all the files present in the folder you are right now. So here you can see the Jupyter Notebook, a Python script with helper functions, and a data folder that will be created once you run the notebook to download the data. Yeah, well, another thing is this panel here on the right. So you can see WEkEO Lab on this panel here, and which is the kernel which contains all the libraries you need to run this notebook. And to run the notebook, you can find two ways to do it. One way is to go to the panel up here and click Run and run all cells. So you can run all the cells in the notebook. And if you want to run one cell at a time, you can go on the cell, click on the cell, and click the play button here. So you will run one cell at a time. So let's get to the Python tutorial. So this notebook has the structure. So first an introduction, quick overview of the libraries and to set up the Python environment, some infos on the data access and the data loading and visualization section. So as I was saying before, in this notebook we will explore the wildfire events during the season of August 2025 in the Iberian Peninsula. The season of 2025 was characterized by hot and dry summers, and yeah, just a second, that created favorable conditions for the outbreak of wildfires. So the first thing we have to do by running this notebook is to import the needed libraries. In this case, we are using some specific libraries for geospatial data, which are Xarray, that is a user-friendly library to manipulate netcdf files. Matplotlib library is a really useful library for plotting, and cartopy is also used for plotting geospatial data, and NumPy, which is a fundamental package for scientific computing with Python. So first thing first, we import all the libraries we need. So you can see some module system libraries, the library to perform data retrieving, which is the HDA that David explained before me, Xarray, Pandas, NumPy, Matplotlib, and cartopy. We also import some helper functions, which you can find in the other file here, the Python script, helper function.py. And let's go straight to the data access. So for this tutorial, we will use two datasets. One is the Copernicus Sentinel-3 SLSTR near real-time fire additive power. And the other one is also from Sentinel-3 SLSTR, but is aerosol optical depth. So to go a bit, to speak a bit about the datasets, so the fire additive power project identifies locations and quantifies the radiative power of any hotspot present on the land, which radiates an heating signal within a pixel of size 1 kilometer square, which is the spatial resolution of the products. The other dataset is the aerosol optical depth, which is a product that quantifies the abundance of aerosol particles in the atmosphere, and then monitors the global distribution and the longer range transport. In this case, the spatial resolution is 9.5 per 9.5 kilometers square. All the observation from the SLSTR instrument on board the Sentinel-3 satellite are available in less than 3 hours from the sensing time. As for the aerosol optical depth, this is applicable only during daytime. So here you can see a little table summarizing the products we will use. You can also find a link to navigate to the WEkEO data viewer, and here you can see the data. So fire additive power level 2 from Sentinel-3 and aerosol optical depth also from Sentinel-3. Okay. So how to retrieve this data? You have two ways, as David explained before. You can use the WEkEO data viewer and download the data manually, or you can use the harmonized data access API to download them programmatically inside like a Python script or a Jupyter notebook. So the first thing you have to do is to create a configuration file where you can put your credentials that you can find in your account on WEkEO. And by running this cell, you can actually create this configuration file just once, so you don't have to enter every time you run the notebook the credentials that will be stored in your system. So then you can download your data programmatically. Once your configuration file is set, the first thing you have to do is to define a request for the configuration with the configuration for the data to be downloaded. In this request, you have to specify some variables that the most important ones are the dataset ID, which is the identifier code of our Copernicus product that we will access, the start date and end date for the download, the bounding box, which are the latitude and longitude boundaries of the study region you are interested in, and some other parameters. So in this tutorial, we'll have to download two different datasets, so we will have two requests. In this case, you can define a dictionary with the two requests. I call them S3FRP and S3AOD, which represent our fire additive power and absorbing aerosol depth. Once you have set your request dictionary, you can actually display your request to see if everything is right. And then we can download the data. To see more details on the download of data, you can click on this link that will send you to the documentation about the Harmonized Data Access API. So the first thing we do is to set a variable to download our data, to perform a request using the search function of the HTA client we set before. And we can actually print all the matches that we set in the request before. So for our range of dates and bounding box, you can see we have 3 items to download. And with matches.download, we can download the data we need in the output path we defined before. So if you run this cell, you will download your FRP data. And you can see them in the data folder here on the left. You can click on data and you will see all the data you downloaded within the notebook. So this request needs to be done for the S3FRP and for the S3AOD. So first for FRP, and the exact same thing we do for the AOD. Mind you that you have to change the variable inside the request it. So the first time for FRP, the second time for AOD. And it's the same process as I already explained. So you match the request and download your data. So here you can see the request. We can see that we also have 3 items to download, and we download the data, which will appear here on the left. So these data are usually downloaded in zip format. So the next thing to do is to unzip them. So this piece of code takes all the zipped files you have in the folder, in the output path folder, and unzip them. And then you can have your unzipped files who's in the left panel here. So we can now go straight to the visualization. So we will first visualize fire additive power data, and then aerosol optical depth data. So Each FRP product is distributed as a folder in .sentry format, which is specific for Sentinel-3 data. And inside the folder, you can find multiple NetCDF files and some metadata. So, for example, you could find this FRP MAware 1 kilometer standard.netcdf, that is the main operation on FRP products. Some more FRP products, let's say FRP SWIR 500 meters, which is the high resolution shortwave infrared fire additive power. Some other files like manifest describing the metadata and some other metadata files and the browse JPG. I will quickly show you inside the FRP folder here on the left. You can see we have all the files I talked about before. So here you can see two types of files, MWIR, which stands for middle wave infrared observations, and SWIR, which stands for shortwave infrared observations. In the use case of today, we will just see the middle wave infrared observations, but all the workflow can be applied also on the shortwave infrared observations. So for this training, we will use just the FRP merged middle wave infrared and shortwave NetCDF, which contains both middle wave and shortwave channels, along with the geolocation and quality information. So the first thing we have to do is to open this data. And in this case, we will use the Xarray library, which I talked about before. And we could use the specific function, which is open dataset, by clicking on the cell below. Here I have set the data path, and I use the function to open the data. Using, in this case, since we are using SCDF, the SCDF4 function. And once you open the data, you can see you have one dimension with 269 observations, some data variables inside the file. So you can see FRP SWIR, FRP MWIR, which we will use today, some latitude and longitude variables, and a list of attributes like title, resolution, start time, stop time, and some other attributes. So once we have opened our file, we can extract the variables we need, which are latitude, longitude, start time, and stop time, which will then be needed for the recording process. The next step is to load the MWIR variable, which we need for today, from the loaded SCDF file. And in this case, we can see the total fire observations, which are 269. And mind you that these FRP observation also include the ones with the reduced quality. And to achieve the actual number of observation, we need to mask out all the non-valid observations. So all the valid pixels are different from -1. And we can use the function inside the helper function .py script to generate, to extract pixel of high quality. So we want to keep all the pixels that are not equal to -1. And we do with this function. So you can see I use the variable I started before, FRP MWIR, -1, which is the flag, the operator, which is not equal to. So we can extract all the valid pixels. And this is the array we get. Now we can retrieve the number of hotspots of good quality, and you can see all the observations were of good quality. In this case, the data array we get is a one-dimensional data array with all the fire occurrences. So the next step is to combine the fire occurrences with the geographical coordinates and bring this information into a regular grid with all the FRP information. The gridded FRP in this case is the sum, or we can say the integral, of variegative power within a grid cell. And in this case also we will use the function slstr FRP gridding, which is defined in the helper function.py script, which can then be used for the auto channel informations. And one thing we have to do before applying this function is to define some variables. In this case, the size of the gridded FRP values for plotting, which is 0.3 in this case. The max integrated FRP value I will have to visualize in the plot. In this case is 500. I didn't say before that variegative power units are megawatts, so these are 500 megawatts. And some geographical boundaries also for plotting. So we can now go straight to our gridding functions. Here you can see I pass the variable extracted before from the file, some latitude and longitude data, the sampling for regridding, the number of fires, latitude and longitude. So I obtain a new array. Here you can see we have some really low values, and in this case we have to mask out also these pixels that are equal to this value. And in this case we can use the NumPy specific function np.ma masked array. So we can mask out all the invalid values, and here you can see the array we obtain is a masked array. One thing we can do is also to compute some statistics to add to the plot. In this case, we have the total number of hotspots, some statistics like sum, mean, standard deviation, min, max of variegative power values, and we put them into a string to visualize later in the plot. Now we can go plotting our observations, which we regretted before. And we can use also another function defined in the helper function.py to visualize exactly the Sentinel-3 variegative power. This function makes use of the matplotlib pcolor mesh and cartopy to integrate the coastlines and borders informations, map informations, and we also can integrate the statistics we computed before. So now we can apply our function to the variegative power we computed before from the middle wave infrared channel, and additionally we can take some information to define the plotting. And here you can see the regridded data for variegative power and some statistics on the right. The next thing we have to do is to load the Sentinel-3 AOD data. The workflow is exactly the same. We open the data with the xarray open datasets function. In this case, the data is also in a .sen3 format, but we have just one file we need, which is the nrtaod.netcdf that contains some geophysical variables for AOD, Armstrong coefficient, some geolocation variables as latitude and longitude, and some quality flags. Once we open the data, we can see that it has 2 dimensions, which are rows and columns. So in this case, we can understand that the data is already regridded. And a long list of some other data variables, which we will need for plotting, and some attributes as before as the variegative power data. In this case, the variable we need is the AOD 550 merged ocean land, which is the aerosol optical depth as at 550 nanometers, latitude, longitude, start time, and stop time. This variable here, AOD merged ocean land, covers all the surfaces, so land and ocean, and already uses quality flags equal to 2 and 3 for water surfaces and equal to 3 for land. And Yeah, as before, we extract some variables, so the AOD merged ocean land, latitude, longitude, start time, and stop time. As before, we compute some statistics, so mean, standard deviation, minimum and maximum. And then using the visualize S3 AOD function from the helper function.py script, we can then visualize our aerosol optical depth product, which you can see here. To facilitate a comparison between Faradative power and aerosol optical depth, one thing we can do is to plot side by side the two products. So here we define some code to plot on the left the Faradative power and on the right the aerosol optical depth for comparison. And here you can see the comparison between the two products. So FRP in the Iberian Peninsula, and you can also see the AOD and its transport up north here. So in conclusion, we use two different products to monitor wildfires using satellite data, which are Faradative power and aerosol optical depth, both from Sentinel-3 SLSTR instrument. And by combining this product, we can obtain a more comprehensive views of wildfire events by linking fire activity at the surface using Faradative power to atmospheric aerosol loading using aerosol optical depth. So thank you for the attention, and yeah, if you have any question, I will try to answer them.
Thank you, Noemi, very much for your presentation. We have a few questions for you. Okay. Let me share my screen. Okay. So the first question is, how is using this data in Python different from calling and visualizing the data from STAC catalog?
Well, I will try to answer the question. In this case, we download the data directly using the WEkEO Harmonized Data Access API. Visualizing them from the stack catalog is a bit different, I think, but maybe I can answer better this question later on.
Yeah, that's fine. We can add an answer to this question in the post-event report. Next question. I think I can answer this one. The notebook is read-only on the Jupyter Lab. I think if you're accessing the notebook from the event website directly on the Jupyter Hub, you can copy the notebook to your personal space to then add modifications to it and run it. Next question is, how can we be sure that the increase of AOD is caused by this specific fire and not by other fires nearby?
Yeah, nice question. We cannot easily identify that this AOD is from the specific fire, but by doing a comparison, we could guess that, and by seeing the transport of AOD, we could retrace back the wildfire event. But mind you that with the AOD, in this specific product, we cannot differentiate between AOD from fires and AOD from dust events. I don't know if Anomaya that I see here wants to answer more deeply this question.
I think you did perfect answer.
Okay, thank you.
Great. Thank you, Anomaya. Okay, well, thank you very much. I think it was the last question we received. Let me just check the chat just in case we have received question there. No, we haven't. Oh, actually, we just got a new one. Can we combine FRP data from multiple sources to have a more detailed timeline?
Yes, nice question too. Yeah, absolutely. In this case, you can have a more comprehensive view of the wildfire events. since you have more coverage between different satellite missions.
Okay, thank you very much. And I think this one was actually the last one. So thank you, Noemi, for
Thank you,
your
Adrian.
demonstration and for answering these questions. So we're gonna take a short break now. So we will be back at 11:15, so in 10 minutes. During the break, you can answer this very short poll that we're displaying on the screen, so you can scan the QR code to access it, or it's also available from the Q&A section of the website. And if you just want to let us know what type of organization do you work or study for, it would be really nice. So thank you very much, and we will see you in 10 minutes. Hello again, everyone. Thank you very much to everyone who filled out the form. We can see that we have a lot of people from university, either working or studying there, I guess. Some people from research institutes, private company, data provider. So yeah, it's great to see that we have such a wide diversity of profiles joining us today. So thank you very much for this. We will go to our next speaker now, who is Daria Andrievskaya from Noveltis, and who will be presenting QGIS tutorial. I can see you, Daria. I will stop sharing my screen.
Okay, thank you. You can hear me as well, I suppose.
Yes,
Okay.
absolutely.
Now I'll share my screen. Do you see it?
Yes, we see it now.
Okay. You see the presentation now, right?
The presentation, yes.
Okay. Okay, great. Hello everyone. My name is Daria. I'm from Noveltis, and today I'll be here to present you a QGIS tutorial in which we will study the wind outbreak in North America, which hit from 19th to 22nd of June 2025. So here on the slide, you can see a little, for the context, you see a little image provided by NOAA, which shows us a time frame of 1 o'clock at night on June 21st. And you can see the wind situation in the area. You can see that the northern part of United States was hit by quite strong winds here. You can see that the red part is by the categories that were defined by NOAA is 4 out of 5. So yes, we're gonna study those winds that occurred in this area at this time, because strong winds are very dangerous because they damage infrastructure. They are reason of power outages for thousands and thousands of people for sometimes prolonged period of time, and of course they are a danger for human lives. So we're gonna study this exact example, and for that we'll use, I will show you quickly this product from WEkEO, which is Era 5 hourly data on single levels from 1940 to present. And we will look at 3 variables from this product, which is mean sea level pressure. Then the second one is instantaneous 10 meters wind gusts. And the third one, of course, is wind speed and direction. So you can go to the WEkEO website and go to the catalog and check this product. Also, just a little note, this presentation is going to be quite quick because I don't have much time, and QGIS usually requires a lot of time by step-by-step procedure. But there's also a PDF file that will be provided to you with a very precise procedure to follow if you prefer to look at it instead of. There's also a video which you can follow. So all the links to the documents, to the data, to the plugin of QGIS, which I will use, also will be given in this document as well. So let's move to the QGIS. So I have this project already open, so I will just show you what we've done and how we've done it, but without like step-by-step procedure, as I already mentioned. So here you can already see the background map, and I will also show you a little plugin which we using to work with netcdf files, which are usually the format of data from Copernicus Marine. From Copernicus Marine Service as well, but from WEkEO too. And here, for example, we have our R5 reanalysis product, in which we have all these variables. I also have a fourth variable here, which I'm not going to use, but it is for you to explore more further and to play around. So this plugin also provided in the PDF file, as I told you, all the procedure, how to get it, how to download it, how to install it. So it will allow us just to more like add the time frames for each variable faster. For example, you can click on this variable, which is pressure at mean sea level, and you click on right-click, add layers, and it will allow you to choose the time frames you want, several, all of them, and quickly import them. So I already did this for you, and let's see what it gives us. So here I have variables each 3 hours. We decided to look at 3 hours frequency from midnight at 19th of June till the 9 o'clock in the evening of 22nd of June. And here you can see mean sea level pressure, with this scale. So in red we have more like higher pressure, in blue we have lower, and I will just quickly show you the evolution. We can see that it was quite okay, let's say, and then from evening on 19th of June we can see some stronger low pressure zones appearing like this. Okay, you see here we see a very, very low pressure at a specific zone. And it will be interesting for us to look because, winds are very correlated to the pressure. So that will allow us to see more in depth this phenomenon. So just to show you how it then progressed, and we can see that by the end of the event, or by the 22nd of June, you can see that more or less the pressure stabilized. So this also the layers are all styled specific way. You can also see that in the PDF file. I'm gonna precise these settings. So what we wanted to do is to choose a specific time frame with which we will work, and we decided that more or less the peak conditions of this wind outbreak, it happened on 21st of June at 6 or 9 o'clock in the evening. Yeah, we kind of see that it's kind of there. So we will stop at this time frame, and what we wanted to do is to see the correlation between the pressure and the wind gust. So wind gust is instantaneous wind gust. So it's not the constant wind speed, but the gust itself. And we wanted to see the correlation between them. And to make it a bit more representative, we also have these wind gusts imported as well. You can see, I will show you the evolution as well. But we just have two variables, two raster layers, we can say. And overlapping them might not be very representative, so we decided to create the contours of this one time frame of mean sea level pressure, which is a time frame which shows the peak conditions of a wind outbreak, and create contours. And for that, you can go to processing toolbox here, which is sometimes not available like that. You just need to click on this little gear icon here, and you just type contours or just contour, just contour. And here in GDAL plugin library, there's a contour polygons, and usually GDAL should be default option for QGIS up from 3.30 version, I think. I'm not sure, but usually it's there. But if it's not there, you can always go to plugin section here and install it. So at the contour, it's here. Here you choose an input layer, which for us is this time frame because we already clicked on it. And then interval between contour lines, I think I did 100 because otherwise this will be too charged. And then you can save it to a temporary file, like it will just exist in this project of QGIS, and when you close it, it will be gone. Or you save it to a file on your computer and then you can use it later. I'm not gonna rerun it, but as a result, it will give you this layer. So here you can see the contours that it produced, and basically the contours function, it allows us to see the zones that are sharing the same values of pressure. So it's basically like geolines, you know, like the altitude, for example, elevation. So for the pressure here, and you can see also the values. And to see those values, you can double click on this layer. It's here. And in symbology, you can change the style of the lines, and in labels, you can adjust the labels to see the pressure specifically on the lines. So like this, you clearly see the lines are going, changing. Like here, it's very rapid change, you can say, because the lines are closer together, like for example, here as well. And this will overlap with our wind gusts. And first I will just show you the evolution. I chose different colors just for you to like distinct them with between this and pressure. So here we can see as well low winds, low gusts in meters per second. They are here like in dark blue zones, and well, the more red the zone is, the higher the wind speeds are. So we can see that as we saw before, during like 19th, it was kind of calm, and then we see that it starts to, well, still kind of fluctuates, but there are some red spots, red zones, and that's exactly from like midday of 20th of June. You see that it increases, like here, it's the very, very red zone, and it progresses like this, kind of stays in this area, a bit isolated for a long period of time. Well, like in our scale of this outbreak. And while it's kind of fluctuates, sometimes a bit higher wind speed, sometimes lower, but well, more or less stays in this zone. And as we looked at the specific time frame, which was 6 o'clock, I think, yeah, this one, we look at this, and well, we see exactly this zone with higher wind gusts, with here a lower one, and what we want to do is to overlap them with pressure isolines that we just created before. So here you can see there, for example, and also you can remember that these zones were low pressure zones, and then it was increasing. And the goal of this mini exercise of like overlapping these pressure isolines with the wind gust at the same time frame, the goal is to see that that both patterns, they might not align, like not match to a point, and the point of this exercise is to show that strong winds, they do not occur explicitly when the pressure is low or when the pressure is high. They occur where the pressure gradient is the strongest. So basically where the pressure changes fastest, and well, yeah, the change is the most prominent. So for example, for the isolines we've created, it is when the isolines are closer together, like they're more packed. That means that the gradient is stronger, and that means that the wind gusts are occurring exactly there. So that's what we see. Like then, like here, we can see that there are bigger spaces between the isolines, and there's basically nothing. Well, quite blue, dark blue regions, and here we can see very dark regions of wind gusts, as well as here and well here, for example. So that's exactly what we wanted to see, and it does correspond to the like physics behind. And the next little thing that we wanted to do, a little exercise, is to create classification raster layer. So basically have an affected area mapping. So to see which zones were hit by strongest winds, like by different kinds of winds. So we decided to have 4 classes of winds: weak, strong, damaging, and severe winds. And to see exactly where they occur. And for this, we will use the raster calculator, because we have raster layers. Well, I already have it used, so that's why. And usually here in inputs, you select the layers you want. And well, I have too many of them. I'm gonna show you just the expression. So you click on expression, and then you will, well, either you will set it yourself, or you will copy paste this one we already prepared for you in our PDF. So basically in this, we will still focus on one time frame. Well, here we decided to focus on at 9 o'clock in the evening for the same date. And basically here you can see 3 classes. So first one, if it's true, it's going to give us 1. The second one, if it's true, it's 2, and then it's 3. So basically the big winds, we decided that they will be marked by 0, and they are less than 15 meters per second of the gust. Then between 15 meters per second and 20 is going to be strong wind, between 20 and 25 damaging wind, and more than 25 is severe wind. So basically this will give us a layer like this. I'll just remove everything. And in this one, oh, nope, here, you can see that in 0, in white, or we can also make it transparent, it's basically where winds were marked as weak, or like background wind, so it's less on gusts. Sorry, that's important to note. Gusts were less than 15 meters per second. And then 1, it is between 15 and 20. You can see that in blue, we have more zones in blue. And then damaging winds are in purple, which are even smaller regions. And the third one, 3, is in red, which is severe winds, which are more than 25 meters per second. Gust, sorry. And it's very, very small region here in pixels. So yes, and this one corresponds to this not MSL, this time frame. Why is it? Yeah. So here, and now as we have this wind classification map, we kind of can see exactly where the winds were the most, the gusts were the most, the strongest, the more damaging than in our areas. And I'll note that even though the gusts were quite strong on the whole area, but still the most severe ones were not covering that big of an area. And to have a more precise classification of this, like we have a classification map which is kind of only visual, and to have a better representation to know like the quantity, like the area in square kilometers, for example, what we can do is we can calculate area of each zone. And to that, first we'll need to polygonize our raster layer, because it's raster, and we need polygons like a vector layer. For that, you choose to go to raster, I think conversion, yes, polygonize. Here you choose input layer, and it's basically you run it, and that's it. And that will be a result, which is not very pretty. And you can see that it also has a background and many polygons. And what we wanted to do is to make it, prepare it for calculation, because also if you open attribute table on right click here, you will see it has many polygons, which we don't even maybe see. And what we want to do is to clean it by dissolving all the polygons by class. So for example, we have this layer, which is kind of the same, but if you open attribute table, you will see that there are only 4 polygons, only 4 classes, which is normal because we have 4 classes in our classification map. And for that, there's a dissolve function. Yep, I think it's this one. Yeah. you choose a wind map that we had before, and you can use option for wind, so it will dissolve by class, so it will see the same class and dissolve it in one big polygon. So for us, it's 4 different big polygons. And before we calculated the area, we also reprojected our layer, which exactly looks like the same one again. But the point is that here, usually, I think by default, QGIS has a coordinate reference system as 4326, which is in degrees, like you can see, but coordinates are latitude and longitude in degrees. And if we would calculate the area straight through the for this layer, on this layer, like on this one, wind map clean, it would give us the area in square degrees, which is not very not very clear, not user-friendly for us. So we reprojected it. If you double-click on it, you'll see that in the information, the projection is the one used for North America, and it will allow us to calculate. You can see that the extent now is not in degrees, but in kilometers. And to reproject it, you can just right-click on the previous layer and export save features as. So basically, you kind of save the same layer under different coordinate reference system, which we choose here. And that gives us another one, reprojected layer. So if we click again on open attribute table, we will see the attribute table with another column, which is called area, and that's because I already calculated it. But you can go to this little calculator icon. And here you can create a new field. And this is very powerful and interesting tool because it allows you to create many different columns in an attribute table. So you can calculate different, many things. And you also have like some options here which help you to get what you want. But I think for us, the formula was it's usually area. Yeah, I think so, like something like, if I just, like this. This gives you area, like you already see a preview for feature 0, which is no wind, or like background wind as we called it, which is a very big value. And then for 1, we have another, second, and third. But what we usually do is we divide it by like this to have it in square kilometers. And like this, you can see that value is way diminished, but also it's quite big ones for 0, which is normal, and quite small, you can say, for the third one. So you click on, you set the name and stuff, and it will give you this area. And yeah, you can see how many square kilometers the wind was affecting. Let me just overlap it like this so we can see properly. Which one? This one. So yeah, you kind of see here that 0 covers a very big area, then 1 in blue less, in purple much less, and in red, which is severe wind, you can see that it's almost 1,200 square kilometers. So that was for this classification map, and a very quick exercise as well is to see exactly the direction and of wind and its speed. So not the gusts, because all gusts it's not the same with wind. And for that, the variables that we downloaded from the WEkEO service is this. So basically, that's the V10 and U10, which are wind components at 10 meters from the ground. And that's 2 components, so to create a vector field. Like this, it doesn't really give us anything like interesting or specific, so we would need to create a vector field. And there's a default function, or it's not like a default function, I think it's a plugin in QGIS that you can use for such vector fields. But well, in my opinion, and to my taste, it's not very clear. And we have this plugin I already told you about. Yep. And it is much cleaner and faster to do such vector fields there. You would just need, as soon as you added the time frames we are interested in, we added for the same we used for the contours, 21st of June at 6 o'clock in the evening. And then you go in this layers tab here, not in NetCDF where you can see all the data about the file, but in the layers. That's basically the tab that shows you all the layers you have added to your project. And then at the end, you see the U10 and V10, and you just choose them both holding Control, you right click, and there's vectorize function. And here you set that two components, you choose that it's a bin, then you choose a downsampling. Well, downsampling basically means how many arrows per, how many arrows you will see displayed, because, well, if you have a very big area, sometimes it's too often, like the frequency of arrows might be a bit confusing, like you don't see much. I think we use the downsampling of 5x5, so instead of 5 arrows, we see 1, kinda. You will see what I mean. And it gives us this as a result. And I just will overlap it with our, with our time frame for the gust as well. So here, just in the arrows, you see, oh no, it's not very clean like that. So here you can see that the color of arrows, it represents the bin speed. So the dark ones are less strong, less strong bins, and the lighter it gets, the stronger they are. And the direction, well, is with an arrow. And we can see the patterns, and we see also that where the gusts are stronger, the bins are stronger, which is logical. And then the gusts are lower, the bins are also low. But also you can see exactly the patterns of bins spreading around. So that's basically it. I think I am still okay with time, but yeah, just to say very quickly, all the files are provided to you. You can repeat the same exercise or maybe even play a bit more. Of course, you can use the same data to the same type of data on another region with our phenomenon of wind or maybe like tornado or something like that. And yeah, there's also in the PDF file there's a little section with further exercises which you can read and, for example, add more variables or play with thresholds for being, like, when we define which wind is strong, which wind is not strong, and so on. And yeah, just check it, and maybe you will find something interesting for yourself as well there. So thank you for your attention.
Thank you very much, Daria. We have a few questions for you from participants. So I will share my screen. The first question is, are the times from the NetCDF in a local time zone or in UTC?
I think it is UTC. You should check it for each product because, well, it might differ for different products. I think for Era 5, when you download it, it asks you, what do you want? Like, do you want in UTC or local zone, something like this? I think I saw this option, but yeah, it depends on the product.
Okay, thank you. The next question is, what DM did you use, and do you think if you chose another one, there would be a noticeable difference in the results?
I did not use a DM for this tutorial because, well, we don't really need it for the bins. I guess maybe you got confused because of contour lines, like isolines, because, well, usually, yeah, DM is depicted in isolines, but no, that was not isolines of, well, of elevation. It was isolines of pressure, just to see to like correlate it better with winds and that, because we could just overlap two raster layers, make one less transparent and one I don't know, just choose some colors, but it wouldn't be very like not that popping, so with contours it was a bit more interesting to see.
Thank you. Next question is about plugins available for use with WEkEO data that can be used with Linux.
Well, there are many, if you're talking about plugins for QGIS, there are many plugins, and I think most of them are developed by the QGIS team themselves. So I assume if QGIS is available on Linux, which it is, then the plugins are available as well. If you're talking about this specific plugin I've used, it is available on Linux as well, but it depends on the version of QGIS because this plugin was developed some time ago. And I'm not sure till which version of QGIS it's still maintained. But I think, and for our WEkEO data, well, maybe there is also other plugins that are available somewhere on the internet, but not aware of that.
Okay. And the last question, oh no, actually we got another one, but the question about recordings, for how long will these recordings be available? They will be available on the WEkEO YouTube channel, and we're not planning on taking them down anytime soon, so for the foreseeable future. Next question is, are the files updated regularly or depending on the map type, temperature, pressure, precipitation?
Yeah, so this all depends on the product. For example, I think the Era 5 has daily, hourly, daily, monthly, yearly maybe. I'm not sure about that. But yeah, but there are other products that might have only monthly or only hourly and so on. But yeah, it depends on the product and sometimes for variables. Sometimes some variables have a more like different temporal resolution than others. You can see that in the description of each product on WEkEO service.
Thank you. And last, I keep saying last question, but we keep receiving new ones. So is it possible to analyze temperature or precipitations data with NetCDF to QGIS?
Yes, I mean, this plugin is for any NetCDF data available. I guess also like from external data sources, not only from WEkEO service as well. And yes, temperature precipitations works as well. It's just about format. Like if the data is in NetCDF format, then it will be good.
Okay. Next question is how can we get the base map, like the country and sea or ocean bathymetry?
So the base map, the background layer you've seen in my project is basically Google Maps satellite hybrid option, I think it's called, which you see when you go to Google Maps and turn on satellite layer on. And this is available, yes, you would just need to add this layer additionally, and this procedure is also described in the PDF file. I didn't stop on it because it was not that important. And they are also like, because you need to add the link, specific link, which Google usually provides, and not only Google, there's also OpenStreetMap and other options. So yeah, this link and procedure to add the specific background layer, as well as other options that you might be interested in, they're all provided in PDF file, so go check it.
Thank you. And the actual last question for today for your presentation, I'm not quite sure this question is actually about QGIS, but it's the following about Sentinel-5P tropomy profile data on WEkEO. Does the platform support visualization of retrieved profiles? And what are the capabilities for spatial and temporal aggregation? For example, creating weekly averages over a specific region.
Yes, this question is not exactly targeted to me because I did not use Sentinel-5P tropomy 1. I'm just trying to recall if I used it before. Probably I did, and maybe in a following presentation the Sentinel-5 is used. I'm not sure, but might be. Maybe we can just leave this question for later. But I think the Sentinel data might not be. You cannot really see it on WEkEO service. You need to download it to see it, like all the satellite images. I think on WEkEO service. So yeah.
Yes, and I think as well, it's also a question that you could ask to Neo, the AI agent on the WEkEO platform as well. they will be the agent will be able to answer this, and if not, someone from the user support team can address this question on here as well. Okay, so thank you very much, Daria, for your presentation and for answering all these questions. And we will now go to the last presenter for today, who is Alexandre Omrin from Noveltis, and who will do a demonstration of an R tutorial. Hi, Alexandre.
Hi, Marine. Thank you very much. I will share my screen and start the tutorial in no time.
Great.
Yes, can you see the screen?
Yes, we can. Perfect.
Perfect. So I'm Alexandre from Noveltis. Hello, everyone. So today's tutorial will be focused on the Etna eruption that happened in June 2025. So the Etna is one of the most active volcanoes in Europe. And yes, on the 2nd of June, there was a powerful eruption in the southeast crater of the Etna. And in this notebook, we will visualize the different outcomes of this eruption, namely the diffusion of the lava flow and also the gas emission, particularly the sulfur dioxide that we'll monitor thanks to satellite measurements. Okay, so we'll be working with R in this tutorial, and here are the essential libraries that will be used in this tutorial. So there are some libraries that are used to plot different graphs and maps that we're going to draw in this tutorial, namely ggplot, rcolor brewer, several packages to manipulate grid data. We will also have the netcdf4 package that is used to read scientific data in the netcdf file format, and other essential data sets such as natural earth and natural earth data that are used to enhance the map data sets that we're going to visualize. So here are some cells that help you install the package that are required and not already installed in the R kernel from the WEkEO platform Jupyter Hub. So you can execute this cell to have the packages installed and available. And with this cell, it allows you to import those libraries. And after you execute this cell, your environment will be ready to run the notebook. So the libraries have been imported, and now we are ready to start. So in this section, I will briefly describe to you the datasets that we're going to use in this tutorial. So first of all, in order to monitor the gas emissions from the volcanic eruption, we're going to use satellite data from the Sentinel-5P satellite. So it is available on the WEkEO platform. You can see it on the data viewer here. And this dataset allows us to monitor different gas emissions thanks to this instrument. So for example, if you go to the data viewer and look at the different download options that you have with the Sentinel-5P datasets in the WEkEO catalog. In product type, if you go down here, you can see that you have several gas formulas that you can retrieve. And in our case, we'll be retrieving sulfur dioxide, which is the SO2 dataset. You have also access to more raw data. Those are like higher level products. So we're going to retrieve this. We're also going to retrieve satellite imagery from Sentinel-2 to just visually observe the eruption and also compute some indicators. You will see that in the later sections. And finally, we'll also use some wind data to try to correlate with the shape of the gas plume emissions. And this is also available on the WEkEO platform. It's a dataset from the ERA5 reanalysis. which is also available on the European Center of Medium Weather Forecasts. So it's the ECMWF here. So here are a few guidelines to help you download the data if you do not already have it available. If you have retrieved this notebook using the Atlas file, the Atlas link, you should already have the data available in your data directory. So here I have the Sentinel-5 image, the Sentinel-2 images, and the wind data. But don't hesitate to use those queries with using the Harmonized Data Access API to retrieve the datasets if you don't already have them available. Just going back to full screen so you can see better the notebook. So now we're ready to start, and in this section we'll take a look at the sulfur dioxide emissions monitored thanks to the Sentinel-5P satellite. So as I've mentioned, this is a program that is dedicated to monitor the atmospheric composition of the Earth. And in our case, we'll be using the sulfur dioxide product. So you can here enter the file name of the dataset, and using the NetCDF4 library, you can open the data and then retrieve the different variables that we want to manipulate, namely here, of course, the coordinates, the time value, and the gas concentration. If you want to look closely at some variables, you can print their dimensions, you can print their values at certain locations, for instance. So you can see that here we have a 2D variable for longitude and latitude, and at this particular point, this is the concentration of sulfur dioxide. Here is the unique time value that we have in this dataset. So we have data on a single date, and you can convert it from this quite cryptic value to a more readable date using this function here. And you can see here that we have retrieved our data on the 2nd of June, which is the date of the eruption. And using this close function, it allows us to close the data and not have it active in the notebook. This will save some memory in the notebook and avoid unexpected crashes. So now we are ready to visualize the data that we retrieve the key variables. So here are the few lines to initiate the map. And here we create a data frame that will be more easy to manipulate. So we can see here that we are creating a table using the longitude and latitude and sulfur dioxide concentration variables. Here only the 10 first rows, but of course we have much more available in the dataset. So here we filter the dataset to zoom in on the volcano. So we filter by longitude and latitude. And finally, we interpolate our data to have our product on a regular grid, which is not the case in the Sentinel-5P raw data. So this is what we do here using an interpolation. So this is a step that takes some time, of course. It's quite big in terms of calculation cost, but now it's finally executed. And finally, in this cell, we just plot the graph and look at the gas emissions on the day of the eruption. And you can see here that we have, of course, this very strong point here that probably corresponds to the crater itself. But you can see that we have, on June 2nd, already a gas plume here that is clearly visible of sulfur dioxide, which corresponds to what was emitted during the eruption. And now, to have a more clearer view of exactly where we are, we can add country borders in R. So you remember that we had a library called Natural Earth, and from this library you can retrieve some coastlines in order to have a more clear view of our geographical location. So we've saved it in a Word variable, and then we can add it to the plot So this cell is almost exactly the same. And you can see that here is indeed the location of the Etna volcano with the plume emitted around it. Now moving on to the Sentinel-2 data. So here in this section, we will visualize first a simple picture, a basic picture of the volcano, and then we'll compute a more sophisticated indicator to locate burnt areas. So Sentinel-2 is a radiometer, so it takes picture. It provides images of the Earth on a regular basis every 5 days. Actually, it's a revisit period. And from this imagery, we retrieve several bands of data. So I can just show you a quick overview of the color bands that are available in Sentinel-2. So in our case, we'll of course retrieve the 3 visible bands. So blue, green, and it's displayed in yellow, but I'm pretty sure that the band number 4 is the red band. Yes. And we also have many bands in the infrared level, and we retrieve also some of them to locate because it will help they will help us locate burnt areas, namely the band number 8, 11, and 12. So you can see them. They are here, band number 8. That is band number 8, and we have 11 and 12 here. So we retrieve them from the Sentinel-2 dataset that we have retrieved. And finally, we will be able to visualize the eruption. So this is an image taken during the 2nd of June. And you can clearly see the smoke here around the volcano. And so this image, of course, has been built using only the red, green, and blue bands. And now, in this next section, we will use the infrared bands to compute the normalized burn ratio. So it's an index that is used to detect burned and disturbed areas on the surface. And as I've mentioned, it is computed using infrared bands. So namely here, band number 8 and band number 11. So you can see that this particular operation is called the normalized difference. So here we compute the NBR index during the eruption. We use the surface classifier that also comes from the Sentinel-2 product to mask the clouds. And finally, we are able to visualize this indicator that we have computed. Whoop. Going back to full screen, sorry. So we can see here that we have masked the clouds over this area. And we can see that when our ratio is low, this corresponds here to the areas where the lava was flowing during the eruption. And on the contrary, around the volcano, we have much darker shades of green, which corresponds to, well, healthy vegetation. Okay, and now we're going to compare those same images and indicators after the eruption to see the difference. So we have a second Sentinel-2 image that is from 2 days later, the 4th of June. And we're doing exactly the same process. We have the aftermath of the eruption here with a very much smaller smoke plume that we can observe here, which well, it's quite contrasting compared to this to the first image, of course. And now we're going to compare the two burn ratio indicators, normalized burn ratio indicators. So we'll recompute it for the second Sentinel-2 image. And when we plot it, we can clearly see here that we had the lava visible during the eruption. and afterwards its coloration is not present anymore. But apart from the lava, we can see that we don't have significant changes in the area, apart maybe from this particular part here. But it probably means that the lava affected areas that were already burnt or devoid of vegetation. And to end this presentation, I will just add some wind data to see if it is consistent with the smoke plume that we had observed in the first section of the tutorial. So here we have our wind net CDF data already available that we have retrieved at the beginning of the tutorial. Same process, we retrieve latitude, longitude, pressure levels, here. And here we retrieve the two directions of the wind speed that are in the product. And with that, we can retrieve also the total wind speed just by calculating the norm of two combined vectors, or the corresponding vector, sorry. So same as before, we gather all of this in a data frame in R. So we have all our variables aligned with each other. And finally, we are able to create the map of the wind. You will see that we have two layers, one for the total wind speed and one with the arrows here that give us the wind direction. So if you remember, the Etna is located in this area. So on this date, on the 2nd of June, we have wind going from going towards the southwest. And if we look back at the gas emissions that we had observed, we can see that we have a plume that kind of follows a similar direction, apart from some perhaps local here curve, but you can see that it clearly goes southwest from the volcano. And I think that we are reaching the end of this tutorial. So I hope you've enjoyed this presentation, and now you can ask me any questions, so feel free to ask. Thank you very much.
Thank you very much, Alexandre. So we actually have one question for you at the moment, which is in which layer of the atmosphere does the Sentinel-5P tropomi sensor perform best for isolating anthropogenic pollutants, the troposphere or the stratosphere?
I don't think I will be able to answer this question. I'm not an atmosphere expert on this side, so yeah, I don't know that. I'm sorry.
Okay, we will address this question in the post-event report then. No problem. Actually, we received another one. Do you use the topography of the area?
No, we didn't. We simply visualized the images provided by satellites, but topography didn't have any play in this analysis.
Okay, thank you. Next question is, how can you use the satellite data, and which missions are the most apt to reconstruct the propagation history of a particular wildfire event from ignition to end?
That's, I think, quite a difficult question, because with satellite data to track such events, first you would have to make sure that you have a short revisit time to make sure that you go to the same area often enough. I will probably go with Sentinel-2 by default, because you have images every 5 days, so to track fires, it can be quite practical, as long as there are no clouds over the area that we are observing. So from the missions, yes,
Sentinel-3 as well could be a good mission because we got a presentation from Anumaya Sundström from UMETSAT on the first day of this event, talking about fire hotspots and smoke monitoring with Sentinel-3. So I think both of these are a good answer. I don't know if Anumaya, you're still with us today, and if there's anything you'd like to add on this. No, I don't think Anumaya is still here, actually. But yeah, I guess both of
it's
these.
probably also nice. I think the issue with Sentinel-3 would be that it flies over the same space, the same area every 27 days, if I'm not mistaken. So maybe if you want to track over time, you may have some trouble, but it probably provides very nice measurements, probably, yes, for these types of events. Yeah.
Okay, thank you. Next question is, can we detect hotspots of forest fire by this method?
I think you probably can if you can retrieve data from Sentinel-5P, for instance, over the area that you're observing. You will probably notice some strong, I don't know, perhaps you're just like in this watching sulfur dioxide emissions. You will probably be able to find areas where the emissions are very strong, and those could be qualified as hotspots, I think. So I hope this answers your question.
Thank you. A question concerning data download in R. I'm using the HDAR package in R to download Sentinel-2 data. Is it possible to download Landsat data the same way?
I'm not sure that Landsat data is available on WEkEO. Yes, I don't see any Landsat platform listed in the catalog, so perhaps that's not available in WEkEO. I think Landsat is an American mission, so perhaps that's the reason why it is not available here. I think WEkEO provide mostly spot or Sentinel data. Yeah.
Yes. Is there a notebook in Python as well? What was the advantage of using R? So there isn't a notebook in Python for this specific topic. There were two other ones for Python developed for this event on other topics. But maybe you can answer about the advantage of using R.
Well, I think that this analysis could be could be done in Python without much trouble. I think both languages are very suitable to perform such an analysis. We did this in R in order to provide a broad presentation of the possibilities. Because we provide QGIS tutorials, Python tutorials, and R tutorials. And yes, for the R tutorial, we chose to provide this subject, but I don't think it has for this particular analysis, I don't think it has an advantage compared to Python. I think you can do this with both languages with no trouble.
Okay. And last question is, the western part of Etna is surrounded by mountains, which might be impacting the atmospheric current. What do you think?
Yes, that is most definitely. This is definitely probable. You can see that from the size of the pixel. I think you can. I don't know if you can still see my screen, but on the wind plot, you can see from the side of the pixel that you don't necessarily capture very small scale wind phenomenons. So, of course, when looking at wind data, we are looking at larger scale wind dynamics and that is, of course, an approximation, but of course, the mountains play a role in the wind circulations.
Okay, thank you very much. I think that was it for questions for you today. So thank you again for your presentation and for answering these questions. Before we wrap up, I will just give you some more information. which you can now see on the screen, hopefully. It's just a quick reminder that you can find all the replays and polls on the event website using the menu at the top of the page. The replay from day one is already available there if you'd like to watch it again or share it with colleagues. It's also available on the WEkEO YouTube channel. We'll send you an email as soon as today's session replay is online, along with the link to the poll for today's webinar. So please keep an eye on your inbox. You will also receive your certificate of attendance by email, either later today or tomorrow. And if you'd like to go further after today's session, I encourage you to visit the WEkEO YouTube channel, where you'll find a rich library of webinars and training sessions from the past few years. You'll also find video tutorials from the ones that we, like the ones we showed today. And you can also discover all WEkEO events, both upcoming and past, through the tab event, the events tab, in the top right menu of the website, where you can open any event page for details and registration. The next webinar will happen on 23rd of June and will focus on some tools available through the WEkEO platform. We hope to see you there. We hope this session was useful to you. Thank you very much for joining. We hope that you now have a clearer understanding of how WEkEO can support the study and the response to natural disasters. We also hope you feel confident exploring the platform, accessing and downloading Copernicus data from WEkEO, and making full use of the tools and services it offers. Thank you again for your participation, and we hope to see you at our next event in June. Bye, everyone.